organizer, for inviting me. All right, so I'm going to talk about a very quick, simple result and kind of a gift to run it. So this is a, I'll tell you why. So this is a simple sublinear algorithms for graph coloring, and I'm going to talk about this thing called asymmetric sparsification. This is a joint work with my incoming student, Helia. All right, but first, happy birthday, Ronit. And I wanted to say, I wanted to thank you, basically. I think I've never been your student, postdoc. I don't think I visited you, and only very recently we started collaborating. But you've been an amazing mentor to me, so I'm very, very thankful for that. And the other thing I want to say, I think almost most of the good thing academically that happened to me was because either you encouraged me to do something good or you discouraged me from doing something stupid. Both was very helpful. I appreciate it. One other thing, I mean, people talked about all the amazing aspects of Ronit's work. Also about the fact that you yourself, I've learned a lot from you as the person you are. And I think, for instance, one example is the Sublinear algorithm community. It's a very vibrant and very friendly community. And I think you've contributed perhaps more than everyone to keeping this community together in this way. So thank you. And this is the only picture I found with me and Ronit, and these are all from hikes this summer. Okay, good. Okay, there were a couple of more, but I see. All right, so now I'll switch to talking about something technical. So I'm talking about graph coloring. You're putting colors from 1 to C on the vertices. You don't want edges to receive the same color on both endpoints. In this talk, n is number of vertices, delta is maximum degree. And graph theory 101, every graph can be colored with delta plus 1 colors. No, you go over the vertices greedily whenever you want to color some vertex here, like whenever it's this vertex turn to be colored. By pigeonhole principle, there is still one color available to this vertex, so we can color it. And you move on. Good. So this gives us the simplest possible algorithm for graph delta plus 1 coloring. But at some point, we ask this question, can you do even better algorithms? And to answer this type of question, you have to go back to the realm of sublinear algorithms. And here I wanted to also, do we have Sohail around here? Okay, good. These animations are due to Sohail. They've been amazing. I've been using them left and right. I want to give credit for that. Okay, good. So you can answer this question. To answer this type of question, can you do better? You have to look at sublinear models like sublinear time, distributed computing, streaming. I will not talk about that, however. Okay, I will just tell you about one theorem we had a couple of years ago with Yu Chen and Sanjeev Khanna that proved the following. This is purely combinatorial theorem. Says that if I have a graph G with maximum degree delta, I can sample log n colors for every vertex from 1 to delta plus 1 independently across vertices. And magically, this still holds that you can color the graph using these sampled colors for every vertex. So every vertex only uses the colors it sampled. Okay, and I'll give you a picture of this in a second. But the good thing is that this theorem, almost as it is, modulo some serious caveat, gives you tons of sublinear algorithms. And the main reason is that after you do the sampling, most of the edges of the graph become redundant. If the two endpoints never sample the same color, why do you care about knowing that edge? Okay, so you throw out those edges, you'll end up with very few edges in your graph, and you solve the problem. Okay, and pictorially, let's say this was the colors you wanted to use. You originally had these palettes over all the vertices. Then what happens is that you sample log n colors for every vertex independently across. Then you can just get rid of any edge. Like this edge is completely redundant. Why do I care about it? No matter what color I use from these two palettes, this edge will never become monochromatic. I throw them out, my graph becomes super sparse, and then I can solve the problem there. Okay, this is the high level view. Yeah. Okay, and then you color, and if you color that way, you find the delta plus 1 coloring of your original graph. All your colors were coming from delta plus 1 colors anyway. Okay, so this is, if you can prove that theorem, you can use it to get tons of algorithms. Okay. The catch is that that theorem doesn't have an easy proof. In fact, it relies on some non-trivial graph decomposition. And in general, the moment you start using this sparseness decomposition, it gets combined with some multi-step approach that you have to color each part of the composition separately. It gives you some not so fun proof. And also the coloring, that result I showed you was a purely combinatorial result. It doesn't say how to find the coloring. Finding that coloring is not that easy. It's not a greedy, simple algorithm. Okay. And for a while, I was very hoping to try to come up with simple versions of the, proof for this theorem, and I failed. And at some point, I gave up after talking with Jeff Kahn and he's a student, and they had this follow-up that they say, okay, we can get ln n number of colors. So they come up with a way of following exactly the same approach, just doing it a lot nicer and more carefully, and getting exact number of colors needed to sample. But there was this part that, like I'm quoting from their paper, that the proof turned out to be much trickier than expected. And from discussion with them, I realized, okay, maybe I should give up finding a simple proof for this theorem. I'm not fully gave up, but for now. Okay. But what we want to do is to do a quick fix, okay? The thing is that this theorem is doing a lot more than what it should do for sublinear algorithms. I'll mention a bunch of things, but I will not go through them, okay? Like if I only wanted sublinear algorithms, I really didn't need something that strong, okay? And this is what I'm going to talk about today. I want to very slightly weaken the statement, okay? And get something which is quite simple and does the trick. This is not going to be a free lunch theorem type of things. We are going to weaken it, okay? So I will not show you a simple proof of that result. I still don't know. But I'll show you a simple proof of something that does the work, okay? And the real motivation for this is come from Ronit. So a couple of times, Ronit asked me, do you have a simple proof of that? Like I want to teach it in a class. And I was like, yeah, sure. Like I've taught it in 3-hour lectures. It's not entirely true also. So I've tried it twice. First time I managed to do one of the 3 parts. Second time, this is 23-page lecture note. I told the students read that. Next time I managed to do the second part of 3 parts. So I feel like if I do it another time, I'll manage to have taught the whole thing in like 9-hour lecture, okay? It's on me. I think I could have done better, but still it's not a 10 minutes proof, okay? So basically, as a gift to you, let me try to give you a 5-minute proof of this simpler version, okay? Good. So what is the simpler version? Let's introduce some asymmetry. And this is the result I want to prove, or this is the result we are proving. I'm going to show we can sample log square n colors on average for each vertex. And then the greedy algorithm itself will just color the graph, okay? So the 2 things that now it is weaker because instead of log n, we are sampling log square n. That's not that big of a deal. The other thing, which is a bit bigger, is that it's now on average you are sampling this much, not into like exactly. But the good thing is that it has a very simple proof and a simple greedy algorithm just colors the graph, okay? So let's prove this. And by the way, this is good enough to get all the sublinear algorithms we wanted. You just lose some log n factors, okay? Some log n factors. Good. So first, what does on average mean? So how do you do this? You're going to do the following. You'll pick a random permutation of vertices, okay? And you look at where each vertex arrives. The position of a vertex in that list tells you what is the size of the colors you want to sample. And you sample something roughly n log n divided by the position of that vertex. Okay, so this is the definition of how many colors you sample per vertex. You look at in this permutation where it appears, and you sample n log n divided by that. And then you are going to sample those many colors per vertices and greedily color them from a smaller list to larger list. So in the opposite direction of permutation. You want to put vertices that have larger lists and color them at the end. No? So that makes sense. So this is how we are doing this. What are the average list sizes? Why can you color the graph? Okay, let's do the first part. Average list sizes are this quantity. Go over all the vertices, sum up LV. Well, this is by definition. This is definition of LV n log n divided by pi v. At this point, you'll see the average list sizes are a small pi. Because this n log n, take it out, you have a log n factor, and then you have a sum of harmonic series, okay? So you get log square. So this way, if we do it, we are going to sample order log square and colors only. Sounds good? The other one, oh, QED. The other one is, let me convince you that whenever you are at a vertex, you can color it, okay? And remember, this is the permutation going in this version, this order, greedy algorithm goes in the opposite order, okay? Let's say you're at a vertex. let's define its back degree as its degree to the vertices that appear before it in the permutation, which means that they color after this vertex by the greedy algorithm. So let's say some of your neighbors that are going to be colored after this vertex V. Now, there's this simple observation that, you know, in delta plus 1 coloring, at the end of the day, you always have color to color all the vertices. So if some vertices are appearing after you, they've not received the color. Those colors are up for you to grab, basically. So this vertex V, at the time, no matter how you color this part of the graph, has these many available colors. Just condition on whatever you've given it. Here, this vertex has these many available colors to choose from, okay? So what do I do with that? Let's assume that my vertex has degree delta. If it is low degree, then you're like completely okay. Okay, I will not prove this part, but if the vertex has low degree, that's very easy. So let's assume it has the maximum possible degree. So I want to calculate that quantity. This is the number of available colors to me. On average, how many colors are available? I have delta, or sorry, on average, how many neighbors appear in the first part of permutation? Well, I have delta neighbors. Each one appears roughly with this probability. Linearity of expectation tells me I have in expectation these many back degree. You do the math, you just plug in the right parameters here, like what is the definition of pi v, you get that you have roughly delta log n divided by the list size. Good. And this is highly concentrated. This is a hypergeometric random variable. You do sampling without replacement. You just say that my back degree is something like this. Why is this good? The very last part of the proof. So let's condition on this thing. What is the chance? These colors are, like, there are so many colors that are available to a vertex. That vertex can, if it picks any of those colors in its list, it can use that color and color itself in the greedy algorithm. So did I sample any of those colors or not? Okay. These many colors are available to the vertex. This is the total range of colors. And the probability that I did not sample any of them is 1 minus that to the size of the list LV that I'm doing. Basically, what happens is that if a vertex has fewer available colors, the permutation ensures that it is also going to sample a lot more colors. Okay. So this is what's happening here. We do 1 minus x is less than e to the minus x. We plug in this quantity. Delta log n divided by LV. The important delta and delta cancel, LV and LV cancel. I have a log n here. Okay, there are some constants hidden around. This is saying it's at most 1 over poly. Okay. So by the time I'm at that vertex, if it has fewer if it has fewer colors available to it, it has sampled a lot of colors as well. We'll be able to pick one of them to color itself. Okay. And that means that you can, with high probability, color every vertex greedily this way. And that's it. You'll get the colorability result as well. Okay. And that's prove this theorem. So you can sample roughly log square n colors on average for every vertex. And now G can be colored even greedily. And that's all I wanted to say. Thank you and happy birthday. Good question. Can we do it in an LCA? So LCA is one of the models I didn't think that much about, honestly. Future work.